Okay, so we wanted to give you guys a review of solving exponential equations. So first thing I want to point out is the exponential quality of equations means that you have that positive base value and you have it raised to a power where x is part of the exponent like you see here. Okay, and so in general, our strategy, okay, what we're going to try and do with these exponential equations is to isolate that original exponential portion that you see. And then you're hoping that kind of one of two things happens when you isolate it. Thing number one is that you can isolate that exponential portion to be equal to another exponential with the same base. So sometimes this will have x in it, sometimes it won't on this other side, but the key thing here is that you can rewrite them so you have the same base number on both sides. So think about that. That's like having something that says, I don't know what power to put on 2, but I know it equals 2 to the 5th power. Then by logic, we can say we know that that must be 5. Otherwise, because they have the same base, there's no way that they would be equal to each other. So we use that logic here. We don't cancel anything out or anything like that. We just know that we can set the exponents equal in this situation to solve it. So we just take whatever those exponents are, with or without x, as long as we have this common base, and we set them equal, and then we finish solving. If you isolate your exponential portion of the function and you don't have something with the same base on the other side, you're kind of hoping that it's equal to just a numerical value. When it's not, you can still use this strategy, and we're going to talk about that in example 3. But then you're kind of stuck. You can't just make an assumption that gets you to the next step. So in general, when we solve equations and we get to a portion where we're trying to isolate something and we need to get it alone, so to speak, in the equation to solve for it, we look to use that inverse operation, the thing that's going to undo whatever's being done to x. So in our case, x is in an exponential function. Okay, so it has exponents as like the function that we're dealing with. So the inverse of being an exponent would be to use logarithms. So here, we want to rewrite the function. And with exponentials, you have all the information to rewrite it one other way, which is in its inverse form of logarithm. So if I were to rewrite what I see here in log form, I would write the word log, and it would have to have the same base that's in that problem of whatever number I had on the other side, and the logarithm would be equal to whatever was in that exponent, which included x, and then you would finish solving from there. So that's going to be our goal in each of these problems. So we're going to look first at this first example. I can see it's exponential because x is in the exponent, and when I see that, my goal is to isolate this portion right here. So the first thing I'm going to do is subtract 4. So I have 54, and then I'm going to divide by 2 because that's not part of the exponential expression. And I have 3 to the 3x minus 5 power equals 27. And then here's what I have to decide for myself. Is 27 something that I can write with the same base that I see as my exponential function has on the left side of this equation, specifically 3? So when I think about 27, it can be written as a power of 3, and so that's what I do. It keeps its value of 27. I haven't changed any value of anything in the equation here. I haven't put anything new in. I've simply written it into a format that's going to help me use that first idea that we talked about, that if these bases are both 3, the only way these two powers can really be equal to each other is if this exponent of 3x minus 5 equals the exponent of 3. And if that's the case, we get that 3x equals 8, and x is equal to 8/3. All right. All right, so we're going to use this again in example 2. I see that it's exponential because I can see x is in an exponent position. It's part of this power with a base of 4, and my goal is going to be to isolate that power. So the first thing I'm going to do is subtract 10. And then once I have this written out, I want to cancel out or this negative 1/3 here. So I'm going to multiply this entire side by the reciprocal of negative 1/3, which is negative 3. So I'd have 4 to the power of 2x plus 1 equals 15. And now I'm at a similar place that I was in the previous example. So I want to stop and ask myself, can 15 be written as a power of 4? But in the world of writing exponents and powers, 15 can only be expressed with nice bases as 15 to the first power. So we're not going to be able to get this same base as 4. Since I can't get the same base, my goal is to rewrite in log form. So I'm going to write log, the base here is 4 of 15, equals 2x plus 1. Now I can solve for x like I normally would. Here's x, and to get x alone, I'm going to need to subtract 1. And very carefully keep in mind that 15 is not having 1 subtracted from it because 15 is part of the number log base 4 of 15. And then I'm going to divide by 2. And it's okay to keep my answer in that format. So I'm just going to keep it as log base 4 of 15 minus 1 over 2. Yep. All right, the final example I included here is because we specifically struggled with this one in class, and I'm going to kind of write the answer out 3 different ways. So here you've isolated the exponential function. I look at it, I have 9 here and 2 here. We cannot rewrite those with the same base. So my option is to rewrite with logarithms. And so here you really have to think about how you see the problem. If you see like this as the exponential function where you're using this base to rewrite it, then this problem would become log base 9 of 2 to the x plus 4 equals 5x minus 1. If I change the way I look at this problem and instead I looked at this exponential and wanted to rewrite it in log form using a base of 2, this same problem could be rewritten as log base 2 of 9 to the power of 5x minus 1 equals x plus 4. And I even have a third option. I could technically apply the log function to both sides of the equation and take their logarithm. So I could have log of 9 to the power of 5x minus 1 equals log of 2 to the power of x plus 4. The answers might look a little different as we complete these different versions of the problem, but in reality their value is the same if you go through log properties and see how they're solved. So remember here we have a log property that says that exponent can become a value in front of the logarithm. And then at this point, this log base 9 of 2 is just a number. So I'm going to actually distribute it. So I'm going to have x times that number plus 4 times that number equals 5x minus 1. And like I normally do when I solve an equation at this point, my goal is going to be to gather like terms on one side of the equation. So I'm actually going to subtract this value because it's a constant without x and move it to this other side. And I'm going to subtract 5x because I want the x's gathered on this side. Okay. So I'm going to have x log base 9 of 2 minus 5x equals negative 1 minus 4 log base 9 of 2. And then notice that both of these have x in common. Even though you couldn't immediately write them as one term, we can factor x out of both of those terms. And as horrible as this might look in one sense, this whole thing right here is just a number. So this is x times a number equals something else. So to get x isolated or alone, we want to divide by that value. And I'm just going to leave our answer in this form. There are ways to rewrite it and possibly simplify it, but we accepted this form from you guys. So that's one way to write this answer. I'm going to go through the same thing if you guys used the base of 2. So again, we'd use that same property. So this would become 5x minus 1 times log base 2 of 9 equals x plus 4. And again, I would distribute this value. So I'd have 5x times log base 2 of 9 minus log base 2 of 9 equals x plus 4. And again, I would work to gather like terms on the same side of the equation. So I'm going to actually subtract x to gather all the x's on this left side. And I'm actually going to add log base 2 of 9 to cancel that out here and gather all my constants on the other side of the equation. So I'm going to have 5x log base 2 of 9 minus x equals 4 plus log base 2 of 9. And again, these two terms look rather complicated, and they are, but they both have x in them, and when you factor that x out, both terms are left as constants, which means that crazy looking thing is just really a numerical value that we can divide both sides by. And then, like I said, there are different ways to write this, but we let you guys leave it in this format. So this is one other way to express that answer, and this answer is the same as the other. It's just written in a different way. And then lastly, we have taking the log of both sides, in which case you would use that exponent property of, or that power property of logarithms, 2 times here, 1 on each side. So we'd have 5x minus 1 is multiplying the log of 9. Now remember that log is the common log and has a base of 10. And x plus 4 is multiplying the log of 2. And we could distribute. So we'd have 5x log of 9 minus log of 9 equals x times log of 2 plus 4 times log of 2. And then we would still be doing the same thing at this point. We're trying to gather all the variables on one side of the equation. So I'm actually going to cancel out this x log 2 in order to bring it over here and be able to combine those x's together. And I'm going to add log of 9 to cancel it out on that side, but bring it over here so that I'm combining together all the constants. So here I have all the terms on the left side now that have x in them gathered together. And on the right side, I have all of my constant terms. And then again, these are complicated, but they both contain x, which means I can factor it out of the equation. And then again, like I've said several times, this looks really, really complicated, and I'm not saying that it's simple, but it is a number value. If you typed it into the calculator, it would give you some decimal value. So we are able to divide both sides by that. And there's a lot of log properties here that you could use to simplify this as well. And you can write any format of them, but I'm just going to stop here and write it like this. All right. And that's going to solve that for us. So this last one we did because you guys specifically struggled with it. So hopefully if you needed to see it again, this helps clarify for you.